Imal also. Anyway, so let's begin. So, a leisure park ride consists of a carriage that moves along the rail track part of the track in a vertical plane and follows the arc like this. Now, what you guys need to understand is that obviously this object, which has this mass, is moving in this direction. And then it says that uh, the velocity of the carriage then decreases 12 in a vertical direction point. When it basically reaches this point, now its velocity is 12 meters per second. Now, with that said, we want to find basically in this part, we're going to skip those because those are energy parts we're going to do later. Describe the change in direction of linear momentum of the carriage as it moves from x to y. Yes. Shazib, can you tell me this? Okay. What is the change happening here? Like this whole thing. Just need to describe the direction. Yeah. Yes, Shazib. Everybody who was here yesterday should be doing this worksheet as I'm doing it, except for Asma and Farina. Yes, yes, yes.
That test it out. Can you just do it today?
What can we do?
That project does testing you took like on Saturday or something.
I
The
didn't,
day we left.
I didn't take it. Oh, yeah, I
So
forgot. I'll take it on Asma. I'll take it on Saturday today. Uh, Let me just, go through. Let me just today. Well, that is interesting. Okay, let me just go through. I wanted to do this, but chalo, you guys can complete this worksheet. I'll check it later. It doesn't matter. You can submit it later. Let's do something because other guy people like. Chalo, never mind. Let's go forward and start. We'll discuss it on later. It doesn't matter. Let's do the next. All right. So I think by this time we are done with. We are done with momentum, and we will be doing force, density, and pressure. So that's the second last, almost like half of this is finished. All right, so let's start with force, density, and pressure, and then we're gonna go forward. Okay, now I think I have started recording this. Fine. Now, you guys, what you guys need to remember is that the third law is one of the most important laws that we have, and it's going to continue for a very long time. So, please write that the third law says that every action has an equal and opposite reaction. Now, this basically is between two bodies. So, what I mean by this is that when you're talking about action, action means, let's suppose body A applies a force on body B. So then the reaction must be between body B and body A as well. So oh my God, body B applies the same amount of force on body A. So what I mean by this is that you should always remember that action and reaction involves two bodies only. Right? So this is something very, very important. Okay, now suppose you have, this is just an example. You have a body, a book, sort of a book, which is placed on a table. So this is a table, and here's the book on the table. And then you also have, like, and then obviously the table is on the ground. So right now we have book, we have table, and we have ground. Now they have shown some forces. They have shown W, they have shown R, P, and Q, like that. Okay. Now they've said this R is the reaction, sorry, normal reaction force, normal reaction force on the book by the table. W is the weight of the book. Now, Q is the push of table on earth, and P is the pull of book on earth. Sorry, that's better. All right. Now the question is that which two forces are Newton's third law pair, which means action and reaction forces. Can somebody please guess? Let me know.
E and Q.
P and Q. Why? Why is that?
Um, it's like push and pull, an action and reaction.
Okay. It's push and pull, which is action and reaction. But why can't it be W and R, or W or Q, or R or P? Those are also forces. Yes, Asma, you have any idea, Abdullah? Any idea? Shazib Zain? One of the answers, Farina said it's P and Q. You can agree or disagree. Wait a second. All right. Now think about it this way. When I started writing, I said Newton's third law basically depends on action reaction between two bodies. Now, why Farina is not right? Because if you look at P and Q, P is a force that is between table and earth, whereas sorry, Q is the force which is stable in earth, and P is the force which is between book and earth. So in these two forces, basically three bodies are involved. Do you get it?
Yes.
Yes, sir. R and yeah. No, Zen is somewhat right, but yeah. So these cannot be those forces. But think about this way: weight of the book basically comes from that the book is being pulled by earth. That is what weight is. So it means that these two forces, which is W and P, are actually the Newton's law pair. Why? Because now if you see, book, the force of weight is between book and earth. Also, P is between book and earth. So earth is pulling book, and book is pulling earth. So action and reaction must only contain two bodies because the third body has no use in it. Do you guys understand what I'm saying?
Yes, sir.
All right, wait a second, please. All right, now I'm gonna go forward, and one by one we're gonna learn about different forces. Okay. So one force that we're going to talk about a lot in this chapter is called the drag force. Now you have done this previously as well, but drag force is a force that opposes motion, and it depends on few things. Number one, radius, which basically controls the surface area of any object. Then it depends on the velocity. So greater the velocity, higher the drag force. I'm going to tell you what this force generally you've studied it with a different name, but just one portion of it. Anyway, and the third thing is the viscosity. Viscosity is basically a measure of how difficult it is for a fluid to flow. Now, let me explain what this is. So, back in the days in IGCSEs, you used to learn about air resistance. So, air is a fluid, and air resistance is basically a term that is given to drag force when you're moving through air. Now, obviously, all these things connect because when you have a larger surface area, air resistance is more. You have greater velocity, air resistance is more. And viscosity coefficient means that now in A levels, we will be looking at different fluids. So, like if you move through water, it would be harder than moving through air. If you move through honey, it will be even harder because the viscosity is higher. Is it clear, everyone? Any question?
Sir, can you repeat it one more time?
Yes. What I'm saying is, Like for radius. Radius means how big the object is because that would control the surface area, right? So a small object would move faster through any fluid, but the big object would have more resistance to the motion. Do you get it?
Yes.
Then comes velocity. Now, if you basically are riding a bike, all right. So, oh my God, my bike has gone. Okay, so if you're riding a bike and you're standing right now, so air resistance will be very less, but as you move faster and faster, air resistance increases. So air resistance or drag basically increases with velocity. You get it?
Yes.
Then imagine moving the same thing, like air resistance is in air, but what if you're moving in water? Would it be easier or harder? Like riding a bike in water would be harder or easier? Would you say?
Harder.
Harder.
Harder, right? What if you are now riding a bike in honey? Would it be harder or easier?
Harder.
Why? Because honey is a thicker material. It has a greater viscosity. Viscosity is how hard it is for some fluid to flow. Do you understand? So in the same water bottle, you can, I don't know about you guys, but in Pakistan there used to be a ketchup bottle that was sold in a glass bottle. Have you seen that?
Yes.
Now
Yes.
it was very hard for that to come out. So you used to just give it a little bit slaps before the ketchup would come out because ketchup is a thicker material. It has more viscosity than water, right? So it means drag force increases with the viscosity. So if it's thicker material, then obviously it would resist more when it comes to motion. Is it clear?
Yes.
Yes.
Okay, very nice, very nice. Now we're gonna basically continue about few things that we already know from IGs, and we're gonna revise those because in this chapter we're gonna use them. First, we're gonna learn about mass, and then we're gonna learn about weight. Then we're gonna learn about volume. Finally, we'll go towards density, then pressure. All right, so these are the things we need. So talking about mass first. So mass is the amount of particles packed in a body. All right. Mass symbol that we use for mass is small m. The SI units for mass are kilograms, and mass is measured by electronic balance. Everybody knows that, right? Let me move this a bit on that side. Okay. Now, weight is the gravitational force acting on a mass. The symbol of weight is capital W. SI units would be newtons because this is weight, and weight can be found out using a spring balance. Spring balance, other name is Newton meter. All right. Then comes volume. Volume is basically the space occupied by an object. The symbol we use for volume is V. The SI units for volume are meter cube, and volume has couple of formulas for regular shapes that we gotta see. Now you need to learn these as well because you will be using these a lot. For cube, volume is length cube. For cuboid, volume is length into width into height or depth, whatever you're writing. For cylinder, which comes a lot, pi r square h. For sphere, it's 4 by 3 pi r cube. This is the most important one. All right. Then the general formula for volume is area times the height. Is it clear? Everybody understand this? Abdullah and Shazib, Zain, Asma.
Yes, sir.
Now, I want to also basically point out here, and that is if there is an irregular shape, do you guys know how to find the volume of that? Must have done that.
Yeah, we'll tie this object to a string, measure the volume before, after, and then subtract.
Yes, that is called water displacement. All right, this is just for they're not going to directly ask you, but if they do, you should know that you can take it. You can put it in a cylinder, and then you can put water into a cylinder, take the volume, then put the object, then take the volume, and then subtract the volume, right? Anyway, so then comes the density. Density is mass per unit volume. The symbol that we use for density is rho. The SI units for density are kilograms per meter cube, and density can only be found by a formula which is mass per unit volume, like that. Just remember, density is unique to each material, which what I mean by this is that gold will have a particular density and it cannot share that number with anybody else. So iron has different, wood has different. So each material is categorized with respect to its density. All right. Then we basically also learn about pressure. Pressure is force per unit area. The symbol we use for pressure is small p, and pressure SI units are pascals, which is PA, or sometimes we also write it as Newton per meter square, so that's fine as well. Pressure has two formulas. So pressure in solids would be force over area. Pressure has rho gh as its pressure in liquids as well. However, there are two important things that we will study in this, but right now I just want to tell you. Barometer is an instrument that helps you find the atmospheric pressure. And then you have manometer, which is an instrument that helps us find the difference in pressure. So that would be everything that we have done in IGs up till now. And from this point onwards, we're just going to go forward. All right. Please copy this down and let me know if you have a question. Today, Caroline is missing and who else is not here? Ahmed Light is not here, and Hibba. All right, you guys done? Should I go forward now?
Yes, sir.
Okay. So now let's go forward. Now, the first thing we're going to learn, and that comes for 2 marks, is the derivation of pressure equals to rho gh, right? So now this derivation is very important. Everybody please note it down. So suppose you have a pool or water. In that, we have submerged a box. Let me just draw the box like this, this. Okay. Now this is the area of the box onto which the pressure of water is acting. Right. Let's say the depth of this is h and the area is a. Right. So first of all, what you're going to do is you're going to find the volume of water on top of the box. Obviously, the volume is this whole volume. So volume will be the area of the box times the height or the depth, that is h. Do you guys agree? So we can simply basically write this as volume as area times h. This is the volume of water above the box. Get it? The next thing we are interested in is how much force is acting. So obviously the force on box will be equal to the weight of water above the box, because water is pushing it down, right? Its weight. Is it clear? Now weight of water can be found out by mg, like that. So I'm writing F because I want force there. The third step in this derivation would be knowing that the pressure on top is going to be P equals to force over area. Now, we know that force here is mg and area we can write it as volume over the depth from this part. Can I do that?
Yes.
Now, let's put it in the formula. So force will be mg. Instead of area, we can write volume over h, like that. Now, because h is being double divided, so I can take it to the top, which means the pressure will be mgh over v. Any issues?
Sir, why did you take H to the top?
Because it's being double divided, right? It is being divided here, so if it's double dividing, it can be multiplied on the top. Do you get it?
Oh, yeah.
Like, like that. Now, if you look at this formula, you see what is m over v in this? Can somebody please tell me that?
Density.
Density. So can we write it as rho gh then?
Yes.
So this is how we can derive that pressure is rho gh. Please write this down. This is very important. This basically comes for 2 marks, not more than that, but still you don't want to lose 2 marks. Anyway, the few things to note in this. First of all, you might see that because pressure is rho gh, so I would say that pressure does not depend on, now they will keep on asking you and testing you on this, does not depend on number one, shape, number two, size, Number three, weight of object. What truly depends on, it depends on number one, density of fluid where this object is. Number two, gravitational field strength, which is the value of G, and the of the depth at which this object is. So if the depth increases, it would increase. So size, color, weight, anything else does not really affect pressure. Is it clear? Zain, you're 100% clear. Shazib, Abdullah, Farina, Asma.
Yes, sir.
Sir, can you
Yes.
explain the second point again? The force on box thing.
Force on, yeah, okay. So basically, I'll make a 2D drawing. So um, you see this is the thing, right? And this is basically the box in 2D, right? And
Yes.
the liquid is on the top. What I'm saying is, obviously, the force that is acting on the top, this force would depend on how much water is basically on top of it. Do you get it? Here.
Yes.
Now, obviously, if you find where is the force coming from, the water is being pulled by Earth, so its weight, water's weight, is going to push the box down. Do you get it?
Yeah.
And how much water's weight? This much water, which is on the top. So, what I've done is I've said force on the box is equal to the weight of water above the box. Get it?
Yes.
That's why I've taken F as mg. Okay, very good. Zain, are you there? And Shazib? Okay, all right. Now, well, now should I go forward now? If you don't mind.
Yes, sir.
Good. Now we're going to basically talk about the next type of force, which is called upthrust. Now, this is completely new for you, so please pay attention here. Now, upthrust is a force due to the difference of pressure on a body submerged in a fluid. Right? So this is the origin of the force, but actually it is explained by this scientist. Is called Archimedes, and we learn it by Archimedes' principle. Archimedes said that upthrust is equal to the weight of fluid displaced. Now, when they ask you for the definition of upthrust, so this is the definition you're going to write, and this is the proof that you're going to do later on if they ask you this. So we're going to basically learn this in a bit. So you can write this definition, and then I'll start explaining this. So suppose we have a water surface here, right? So let's call this water surface. We're just taking it as the fluid. Within this surface, we have an object that is placed inside like that, okay, completely submerged. Now, Naturally, what you should understand is that this portion, this part, is the top, and that would be the bottom. Now, of the depth till the top, let's call this HT, and the depth till the bottom, let's call this HB. Do you guys agree?
Yes.
Just by looking at the depths, where will the pressure be greatest, top or bottom?
At the bottom.
Bottom.
Bottom. And the reason is that pressure depends on the depth. So we can say that the top pressure, if it's this much, then the pressure at the bottom would be much higher, like that. And it will act upwards. And the reason is that pressure basically acts from all sides, like that. So we can say this is the pressure at the bottom. Let's make it equal. Now on the sides, it's a different story. On the sides, what happens is that the pressure keeps on increasing slowly, and because the depth is increasing. But it is also happening on the other side as well. So on the sides, the pressure is completely, just doing no net effect because it just cancels out on every point. But there's a difference of pressure from bottom and top. Do you guys get it?
Yes.
Naturally, we also understand that pressure causes force. So if there is a higher pressure at the bottom, so the force at the bottom would be bigger than the force at the top, which basically will try to cause upthrust. Upthrust means it is trying to move this object upwards. Is it clear? And whenever you go swimming, you might have experienced this as well. You enter into water, the water tries to push you up, and that's how you float, right? Do you guys get it?
Sir, even if you like try to submerge an object, it automatically gets pushed upwards. Is that upthrust as well?
Come again, please.
Like, for example, if you try to submerge an object underwater, like I've tried it before, it automatically gets pushed upwards.
Yes, that is exactly what upthrust is. Do you get it? Now, in reality, why is this happening? This is happening because what you've really done is you have taken up this much of the water's volume. Do you get it? And because of taking up this volume, water has been displaced from here. Do you get my point? And because water has been displaced from here, the water wants to regain this volume. And that is what causing water to push the object out or upwards. Is it clear?
Yes.
Right. Now, there's a simple derivation that we're going to do now for upthrust for understanding what exactly it is. So I'm just going to write the derivation. This is our main purpose today to prove that what Archimedes has said is true. All right. So first of all, we're going to look at the pressure difference. The pressure difference is basically change in pressure, that is pressure on top, pressure on bottom minus pressure on top, like that. Right. Then the difference in pressure, then bottom would be pressure is taken as rho g. Can I say HB because it is the depth till bottom minus rho g HT. Everybody agrees? Please let me know if that is clear.
Yes.
Okay. because the density is the density of this density that we're talking about is the density of fluid. So, and the G is the same. So I can basically take rho G as common. So I will get HB minus HT. And if you notice, this difference is this height only. Do you get it? That is the length of the object. So we can say the difference pressure depends on rho G delta H. Can I write it like this then?
Yes.
Okay, very good. Now let's go forward. Since we know that pressure itself can be written as like change in pressure will be equal to change in force over area. So we know change in pressure is also we just found out to be rho G delta H. Can I say that? See that?
Yes.
If I multiply A on that side, so the change in force, which is the difference of force pressure of top and bottom, or force of top and bottom, can be written as rho G delta H times A, right? So this is the area, right? Area of this object. What exactly is this? This is basically volume. The change in volume will be basically the area times the change in height. Do you guys get it? Like that. So the difference in force now can be written as rho G delta V, and this is the formula for upthrust. Understood, everyone? Where I would like to tell you that this is the density of fluid. It could be water, it could be anything. This is the gravitational acceleration of field strength, and this is the volume of object, or I could say, which is also equal to the volume of fluid that is displaced, because the same volume of fluid would have to locate somewhere else, because now this is the amount of volume that is gotten into it. Do you guys get it?
Yes.
Okay. Now proving the last thing before we leave, and that would be proving Archimedes' principle. Now, Archimedes' principle says that it is upthrust is equal to the weight of the fluid displaced. The formula that we've just learned about upthrust is that upthrust is rho g change in volume, and I've told you this volume change is the volume of water displaced. Right now, think about this way: density of fluid will be mass of fluid over volume of fluid. You guys agree? Mass of fluid over volume of fluid that is displaced, right? So if I put it right here, can I say it is mass of fluid divided by the volume? The change in volume is the displaced volume times delta V. This and this will cancel out. So what you get upthrust will be mass of fluid times G. So mass of fluid times G is basically the weight of fluid that is displaced. And that's what Archimedes' principle says. Is it clear? So these two derivations and the proof is within the course. They can ask you. Usually, upstairs derivation comes for 4 marks, so it is one of the most important ones. So if you still have any doubt in this, do let me know so I can clear that up. Okay. All right. Then everything is clear. Shazib, Farina.
Yes, sir.
Yes, sir.
All right. Asma and Abdullah, everything is done.
Yes.
Okay. Now, because Asma was basically in a different city, and Farina